All right, let's get started. Hello, everybody. Thank you for the last session of today to attend still. I hope you're still mentally a bit awake. I was asked by Mohammed to talk about reproducibility. So I prepared an hour-long rant for you of my point of view on reproducibility. To be a bit more uplifting in the end, I called it improvements that add up. So hopefully we'll learn some methods, some techniques that help us to achieve real progress instead of, just having the illusion of progress like in this ESSIR painting in the background. So quick word, who am I? I'm a third-year PhD student here at the UVA at the IR lab, supervised by Martin de Rijke and Onno Suter, who is at Booking.com. Before that, I was a data scientist at Blinkes in Berlin, did my Masters of Science there at the Hasse-Plattner Institute in Potsdam, and generally my research interests are unbiased learning to rank. I think you'll hear something about this on Thursday, user simulation and offline evaluation. So, before we get started, one important thing to acknowledge here, there has been a really nice tutorial on the topic of reproducibility in natural language processing and also in IR, given by colleagues at the IR lab and by the organizers, what is now the Machine Learning Reproducibility Challenge. So some parts of this little rant are based on this. So I want to just acknowledge that this is a really great resource. All right. Let's talk reproducibility in IR, and I would argue that there is a crisis at some point, or at least regularly. I would say every 3 or 4 years, we'll have a big paper at an IR conference that basically shows that nothing is working. So you might be thinking, what crisis, Well, I would say that the big intervention was in 2009 in ad hoc retrieval, which is basically you type a search query, you want to get some results in the moment. And there was a really big paper from Armstrong and colleagues where they surveyed basically all the SIG-IR papers and CRKM papers on ad hoc retrieval over a decade, and basically found that on the track data sets, they did not improve at all. Every individual paper kind of showed significant improvements over their baselines that they used, but in the end, they found, well, the improvements don't add up to progress in the field. So each paper had kind of really weak baselines where they would improve upon, but they weren't properly comparing against kind of the strongest methods that we would have in the field. And so they concluded the improvements don't end up. So hence also the title of today's talk, hopefully we find some improvements that do add up. Another intervention was 10 years later in rating prediction. There, Steffen Rendel and colleagues reproduced 10 recommender systems that all tackled the movie lens 10 million data set. So a very popular, very old data set, very commonly used. And all of these papers that you can see here used kind of very standard matrix factorization as baseline. So these are in black here on the graph. And these were the 10 methods that were proposed in blue. And you can see all of them are kind of better than the baselines. And what the team did was basically, well, first of all, they looked at these baselines and just tuned them. So where did we arrive then? So then we had much bigger improvements. So this is RMSE. So rating prediction is accuracy metric here. So lower is better on root mean square error. But what they also found is, well, if you use properly kind of tuned extensions of these old methods, for example, coming from the Netflix competition around 2009, you outperformed all of the methods that were proposed at big conferences, ICML, NeurIPS, SIG-IR, these kind of things. 2019 was not a great year for recommendation, I would argue. Or maybe it was, but like at the same year at Rexis, this was the best paper. A survey of 18 neural recommender systems. So these were published also again at big conferences between 2015 and 2018. And first of all, the authors found, well, only 7 out of 18 papers that they surveyed could be reproduced, meaning code is available, things run without major complications. 6 out of those 7 papers could be easily outperformed by very simple heuristics. For example, user-based KNN, item-based KNN, things you've heard probably today in the Rexis lecture in the morning, or graph-based random walk methods. There was one paper that was significantly better than these simple heuristics. That was back in the day, the Netflix VAE paper for recommendation. But even that was not consistently outperforming a very strong linear method, something like SLIM from 2011 it is. So this was kind of the catchy title. Are we really making much progress? And yeah, so it basically obliterated neural recommendation in 2019 for this part. And there are many more examples. I won't list all of them, but we've basically seen these kind of interventional papers in IR in session-based recommendation, in next kind of shopping basket recommendation, neural IR, sequential recommendations, learning to rank, unbiased learning to rank. So there are always different things. Typically, there's something like complex methods get beaten by very simple baselines, but there are also some really interesting stuff. Like, for example, from Alexander Petrov, who's also here, a really interesting highlight that the implementation of a baseline, in this case, BERT for rec, really matters, and the tuning procedure really matters to get kind of the best results, right? But we are not alone in this. So this reproducibility crisis is not only IR, it's larger machine learning. So there have been really big papers in deep reinforcement learning, GANs, where they basically show that most GAN extensions don't matter at all. Metric learning, bandits, computer vision, time series forecasting, NLP. So quite a bit of a dire outset, but let's see what we can learn. Why would we care about this? Why would we care about reproducibility? I really like this quote from David Scully from a ICLR kind of paper. So that's the only one I'll read out today, but it's a truism within the community that at least one clear win is needed for acceptance at a top venue, yet a moment of reflection recalls that the goal of science is not wins, but knowledge, right? So this echoes kind of the thing, we should care about reproducibility because that's how we make progress, right? We learn something, we have lessons that generalize, we actually have results that other people can use and reproduce. What is reproducibility then? So I've said this term probably already 20 times. So what is it? Well, the ACM defines it at all of their major conferences in these three things. Repeatability, which means the same team can run the same setup, which basically means you can run your own code a while later, which is often, not already the case, and that you get the same results, obviously. The second one would be reproducibility, which means I can clone your Git repository and run it and get the same results. And the last one is replicability. So somebody else takes your idea or your code and applies it to something completely different and also gets the similar results, right? So your lessons are being replicated here. What's the problem with these definitions? Well, not everybody agrees on these definitions. So at NeurIFS, we have different definitions. They don't look at teams and setups, but they look at data and setup. So for them, reproducibility is same experimental setup, same data, which is not what we had at the ACM. Replicable, same experimental setup, different data. Robust, different experimental data, same data. And generalizable, different setup, different data. That's not really helpful, right? So just be aware if you're submitting to different conferences, you should use their definitions. But for this talk, I don't really care about what kind of definitions we have. I think what is more interesting is that we have similar notions, right? So reproducibility is this kind of elusive concept, but some core ideas are similar. First of all, we want to be able to rerun code. That's already the first step, which most people think about reproducibility, right? Second of all, we want to be able to re-implement an idea. So typically that does not require that your code is public. It's better that your code is public, but it definitely requires a lot of detail that I, for example, can just read your paper and completely re-implement it from scratch. And third, we want lessons that generalize. So we want to draw similar conclusions in a completely new setup, on a new data set. That's a very fancy term. No, on a different setup, right? So we want to have, that's what I would argue is actual progress, right? So lessons that generalize here. I'll leave you with one more definition, which I think is useful from a different survey paper, but it also agrees with the ACM definition, which is Reproducibility is the ability of independent investigators to draw the same conclusions from an experiment by following the documentation shared by the original investigators. So I think that's a very useful way to think about these things, because it stresses certain things, that there are other people involved that want to say draw similar conclusions by following what you kind of publish into the world. So this is what I want to spend kind of the lion's share of this talk on. Discussing which things, in my opinion, so also big disclaimer, this is an opinion, right? So this is all my view, makes a paper not reproducible. Then we'll talk a bit about how can we fix this, but a lot of things are just the opposite of what I list here. So I won't go through every single point and tell you, like, do the opposite. So this is kind of the same in one section. So what makes a paper irreproducible? The first thing is the documentation. So in 2018 at AAAI, there was a survey paper of 400 papers in AI between 2013 and 2016, where they just looked at what was documented in the paper. Here, documentation is a bit loosely defined. It's also about, like, did they publish code and things, but essentially what they found was like 47% of papers only had a clear problem statement. Only 22% of papers formalized the objective that they were trying to solve, or added research questions, like only 6%. Granted, this is a while ago, but still, the paper got a lot of traction back in the days. Only half of the papers included kind of the trained data set, only a third then the test set, and results were almost never shared, right? Like the metrics that you basically obtain as like a file. Lastly, experimental setup. A lot of papers describe this, but then only a third describe kind of the hardware specs that they use or release the code. I would argue these numbers are much higher nowadays. Like, it definitely goes up. There is a good trend. And also the authors search for very explicit mentions of terms. So this should be a lower bound. This is probably way too low. But still, back in 2018, this was an important finding. So why is insufficient documentation kind of a problem? And why is it a problem if we don't have, for example, a problem statement? So this comes to the scientific method and how we test an hypothesis. So remember, 47% of these AI papers only included a problem statement, the rest didn't. But if we're honest, how often do you start a project without having a clear problem statement or research questions in mind, right? So typically we are like, oh, this sounds interesting. Let me run some baselines, and then I have some idea and we'll build on top, and it doesn't work, and some other idea, and then it's maybe better. And then you kind of work until it's like good enough, and then you write a paper and then you publish that. What's the problem of this approach? So first of all, this is really unclear what research questions were you solving from the start. And this process of like continuously just testing stuff and like, trying to get small improvements, that can lead you to very wrong conclusions in the end. And it's also a lot of wasted time, effort, and computational power. So I would argue at least a rough version of your research questions should be like set from the get-go before you run any experiments. Because what's the problem if you don't? This comes to the wrong conclusions part. There is a lot of problematic hypothesis testing in science, well documented also in other fields like psychology, for example. Some of them are quite malicious. I don't want to go into that direction, but so for example, cherry picking refers to the thing that you only include results in your paper that kind of support your hypothesis. That's obviously a bad thing to do, right? P-hacking is analyzing the results in so many different ways until you find something that's significant. My favorite term is fishing expedition. That's basically when you just analyze your data in all different directions to just find something that you can then report without having any hypothesis at the start. But for example, what I would argue, what happens way more often is something called harking. You find a significant result in your data, and then you slightly change your hypothesis and your question in a way where you're like, this was the thing I wanted to find out all along, right? And then you just write a paper about this. So this can also happen a bit subconsciously, that we change the questions for which we have results, actually. Note, this is not the same as having an exploratory data analysis. We obviously often analyze data, find some interesting things, and then we want to write a paper about this. But there we are up front. We write like, we analyze this, we find this, we design an experiment, these are the results. It's not the same as running an experiment, finding result, and then pretending we ran a different experiment from the get-go, right? So this is important when it comes to harking. This obviously also brings us to statistical testing. And here I just want to stress that in the age of deep neural networks, just comparing the means of two models is not enough anymore to say, you know, model A is better than model B, especially in ML, where we have a lot of evidence that you can get into a local optima that does not generalize necessarily well, or you're just there by chance. There's a lot of really good work on this. So I would argue, if you can computationally, always compare your models across different seeds and on different data sets, right? If you have different data sets, formulate a null hypothesis per data set. Correct for multiple comparisons if you compare multiple models. Don't just have a fixed significant level and then just, you know, do as many tests as you want. We saw a bit of, I won't discuss specific statistical tests here, but there is some good work in the IR community that by now, for example, Wilcoxon or sign tests should be largely avoided. Like I linked some literature there. And then in the end, it comes down to report what you're doing. Report the test, report the significant level, and add confidence intervals. I did so many reviews in the last recent weeks where people just didn't do that and say like, we are significant by 0.05, and you don't know which test was used. Was it two-sided? What does any of this mean, right? I linked some literature here for really good discussions of statistical testing in IR. Unfortunately, I couldn't link like a really great hands-on Python tutorial or something that just gets people going and does everything right. I don't think that exists yet in IR. If somebody knows, please tell me. If somebody wants to do this and has a stats background, feel free. I think that's a big kind of open opportunity. Well, let's talk about the thing everybody thinks about when they think their paper is reproducible or a paper is not reproducible. It's typically code is released, checkbox, it's reproducibility, right? This is what we do. We publish code. We write something in our paper, a line like, the source code is here, and then we link some GitHub repository, and then I click on the link, and this is an actual repository, right? I obviously did not disclose who this is, but it just, this is infuriating, isn't it? Like people will be like, this kind of thing of like, we will publish the code on acceptance. And then you get this. This is not as uncommon as it might seem now. So in a really good study from last year, there were 21 recommender systems papers analyzed. 12 out of them only linked a repository. 2 out of the 12 links led to an empty or non-existent repository. So even if the code is published, that's the second point. So it's often incomplete, it's missing, or there is some code. But what does publishing code and all the code actually mean? So I think a lot of people publish their core experiments or their core method. But if we're honest with ourselves, how often do we publish like everything that is like executable or everything that we did, right? Data sets, all the splits, all the pre-processing steps, baseline code, the hyperparameter tuning for our baselines, all the method details, not just the skeleton, not just something like that looks like our method, here's some pseudocode. Dependencies with exact versions, the scripts to orchestrate our stuff. Maybe we sometimes even don't have them. We should have them. It's much better to reproduce them things. And then sometimes this is especially, I think, a thing known to many of us for data. Try downloading a data set from 5-6 years ago. Like oftentimes you just run into like some non-existent URL anymore or something like that. So sometimes we also publish things and then they're just on stale URLs and we can't access things anymore. Another thing, now it gets very like kind of subjective, but I would also argue code itself and code quality impacts reproducibility. So if you have code, understanding your code is a big part of understanding your method. It makes your stuff reproducible, right? What can, in my opinion, impact code readability? Horrible formatting. We've all been there. We've all seen this. It's not great to follow a paper like this, right? Large amounts of commented code. Sometimes people code like comment big chunks of their file for different experiments. This is literally what methods and if statements are for. Just deeply nesting stuff. Having a high amount of copy-pasted redundancy, insanely long methods and very complex files, right? Or they do something very unforeseen, something, you know, like an important deviation where you would expect something obvious, and then they don't explain it, like no comment there. Like you don't need to comment your code line by line, but on the important stuff, like tell people what you did here. And then the last point, that's also like, I think that's where I fall also, like you can also be too modular. Like if you force everybody to open like 30 files to just understand your method, it is also horrible for reproducibility, right? So you can also be too clean in a way, or like to try to be too fancy and write the next library. It's also not great, right? So without just ranting, I also included some things. These are not things that I initially wrote, but my co-author just screamed at me when I asked him for feedback for these slides. He was like, oh, so what about all of this stuff you said for the last 2 years? So here are things I think that help quality. Using the Python style guide. So if you write Python, name stuff like things should be named in Python and not, you know, uppercase function names and these kind of things. Use strict formatters if you don't care about formatting. Remove unused code. Catch bugs with linting. Like and delete commented code. If you need an old method that you've used before, commit it to Git, delete it. You can always go back. That's literally what Git is for, to have a history of your code. Don't keep commented stuff in there, especially not in the final release. If it wasn't necessary for the paper, drop that stuff, right? Use environment managers that can have reproducible environments. So I hate Conda for the life of me, but sometimes we have to use it. Mumber is fine in this regard. Poetry is better. Also, sometimes I would argue, try to not create too many intermediary files on your system between experiments that you want to run, because you force somebody who reproduces your code to like follow basically the trail of all of these six, 7 different steps that you did, right? So try to avoid that as much as you can, unless you absolutely need it. Write scripts that orchestrate your stuff. And if your project gets too large, break it up, right? So I think these are all little things for making your code a little bit more reusable for future projects, and also to go back to your stuff and just being like, this is what I did, right? Like sometimes we don't understand our own code a little while later. I also realize I'm going basically way too far. I'm sorry if I'm just rambling. So please, if you have any questions, feel free to stop. So this was on code, right? On like how code can impact a paper to be not reproducible. Let's look at what makes your code run, but I get different results. This is typically uncontrolled randomness or variability kind of. And I would argue there are 2 different ways. The first one is randomness that we have in our code through design decisions. These are things like we use neural networks, we have random weight initialization. If you initialize your neural network and I initialize a neural network, we get different weights, right? Then we use stochastic operations, dropout layer, noisy activation functions. We use algorithms that have stochasticity built in. Random forest has a random feature selection built in. But then also on a different level, data sets, the way we split stuff, the way we shuffle our data, the way we order batches when we train our model. These have all tiny, tiny effects, but they can change the results, right? And maybe we've used the hyperparameter tuning method. There's also stochastic. For example, like a Bayesian method. The last part is also worth mentioning. It was very briefly touched upon today in the evaluation lecture. Some people, because it's too computationally expensive, sample IR metrics, meaning computing NDCG based on a positive document and, for example, like 100 random negative samples or something like that, instead of computing the full NDCG over your entire ranking. I linked some discussions about that from Google. They are often inconsistent with the proper kind of slow computation. So be a bit mindful about that. And if you sample metrics in your code, they can obviously also lead to different results based on who is executing this. So overall, fix random seeds in your code, release the code, and release all of your data sets. What's the next thing? So this is randomness through implementation. The first one were things in our code, design decisions that are stochastic. But there are even more things that lead to different outcomes, right? The way we implement our things. So for example, the random seed for our pseudo-random number generator, we've already covered before. If you use NumPy, PyTorch, JAX, whatever, you need to fix this. Then the framework itself leads to a certain kind of stochasticity. JAX and PyTorch initialize neural networks differently. So depending on how you implement things, you will get different results. And not only that, but different framework versions, unfortunately, also lead to different results. This is courtesy to colleagues of mine, Sami Julia and Romain de Fayette. They trained the same RL algorithm over 3 different versions of JAX. It's the exact same model, and the reward goes up. One model just completely collapsed, and that's just a different JAX version. There was a bug in the background. So it's really important for people to know if you use JAX 4.2.1 or 2.3, right? So these things need to be reported. Next thing, running the same code on 2 different GPUs leads to different results. So also always tell people what kind of GPU you use, because there are different optimizations, there are different hardware requirements. And then it gets a bit in the nitty-gritty in the end, right? So like if things execute in parallel, you have some non-determinism there, you have different compiler settings and hardware rounding errors. I don't think they're necessarily that important. I think the most important one are the first 3, which are random seeds, framework version, and what kind of GPU, for example, you use. So report all of that. I think it's good. So let's talk baselines. Baselines, if you read a lot of IR reproducibility papers, is probably the #1 complaint about why nothing is working, why aren't we making any progress, why is everything horrible. That's basically every few years a new Rexis paper, a new SIG-IR paper that claims like nobody understands how to do anything anymore, nobody can tune baselines, everything is bad. So we'll take a bit of time for baselines. What do I mean with problems that we have with baselines? The first one is baselines are unavailable, right? That means maybe you just copied results from a different table and said we use the NDCG reported by these people. Then you didn't run any baselines, right? Maybe you didn't release the parameters that you tuned your baseline with, or the code is not there, right? In all of these cases, if somebody wants to reproduce a work, the baseline is unavailable in the setting. The next thing is an untuned baseline, right? The classic line of we use the same parameters as X, Y, and Z. It's not tuned. It's like in very rare cases, you can get away with that. Like if you use, I don't know, insanely complicated transformer models and you just use the similar architecture or something like that. But even then you should do some tuning. Then something we will discuss in more detail, the lack of a simple baseline, things like simple heuristics are missing in your comparison, lack of strong baselines. For example, the example from the start that you don't have linear models in your comparison. And the last part is incorrectly implementing a baseline. So not only you not making any mistakes, but sometimes use a framework that has errors in them. So there was a really good study from Google on LambdaMart, which is a state-of-the-art ranker in my field, implemented in 2 different settings, in LightGBM and in RankLib, a Java library, widely different results, like 10 points NDCG different results. So if you use the RankLib version and you improved on that, then you're state-of-the-art because you beat LambdaMart, right? So this all matters, correctly implementing baselines. All right, let's talk about the first one, about untuned baseline. And it's one of my favorite papers from last year. It's from Rexis 2023. And there, 21 recommender systems were surveyed from major conferences from 2022. First of all, 6 out of 21 papers did not have any information about the hyperparameters and about the baselines at all. 4 papers just copied parameters from previous work. 4 papers, use the same parameters, but then on all the data sets, which is something you shouldn't do, like certain things, like an embedding size, like a learning rate. These are expected to vary for different data sets. 7 out of 21 papers list parameter ranges, but then didn't say how they found the best parameters. Like, how did you tune this? Is it grid search, some Bayesian method? What did you do, right? So only 2 papers described everything: parameter ranges, final values, tuning method, tune across data sets. And then 1 of the 2 didn't release their code, right? So kind of a dire picture that only 1 out of 21 papers did everything correctly. They looked into the 7 papers further that tuned their stuff, or gave them parameter ranges where they could say like, okay, this we can try to reproduce. And they did a very interesting analysis where they showed basically that when they tuned all of the models and they ran the methods with random parameters essentially, And what you can see here in the table on the bottom is the performance of the models when they were untuned, and on the top, the performance of the models when they were tuned. What is important to note here is every model, even the worst one, when it was tuned, beat all of the untuned models. So essentially, if you only spend a lot of time on your own method, but no time on baselines, you can show what you want. This is not a tip. This is concerning. So they had this very lovely paper about they said, well, everyone is a winner. Congratulations. It was a very passive-aggressive conference talk when it was given, but it was really good. So the point here is really, you can show whatever, and that's kind of concerning. So you should be really concerned when people don't tune their baselines, right? Okay, let's take it back to, it was before Christmas, so sometime in December. This is a Slack message with my co-author Romain, after we worked on a project for over 2 months, a reproducibility study of everything. And he sent me this thing of like, what do you think of this performance? And it was very early, so I said mediocre instead of average. But so what I wanted to say is like, yeah, that looks kind of like the performance we see every day. This is not, I didn't know what model it was, but these NDCG, these DCG values and these MRR values kind of look like the things we saw for the previous 2 months. And then he sent me this other thing, which was much better. Like, look at the MRR differences. It goes from 51 to 58. That's not an improvement you see every day. And this was NumPy random uniform, basically shuffling. This was really bad. So this was a base model that we were using for 2 months. And we didn't figure out that we were evaluating all of our stuff below random. So this entire pre-trained base model was broken. So this is on the importance of simple baselines. They can help you uncover completely fundamental flaws in your setup and help judge your overall performance gains. This was the final kind of part of the reproducibility study. So these was a BERT ranker released at NeurIPS. In the end, we did some tuning of this. The dotted gray line is random performance. So all of these things in the base model stayed below random, which is not great. So a random ranking is a really good baseline to always compute at the start. A popularity-based ranking, if you're doing a recommendation, is a really good thing to include. If you're doing neural IR, BM25, things like query likelihood, these kind of insanely basic methods are really good to calibrate your stuff. And if you're doing recommendation, KNN-based methods, random walk-based methods, just to have, to calibrate your expectations. Where are you on this data set? It's really good to have. Now let's come to the importance of strong baselines. And I would argue to claim state of the art, you need to compare against very strong baselines. And typically these strong baselines are also not just from your model class. What I mean with that is like, if you want to have state of the art in recommendation with a neural network, you really need to have a strong linear model in there. The best baselines depend on your task, right? Even on the implementation. So it's really, for learning to rank, you need to use light GBM lambda model, nothing else. That's the stupid thing, but that's kind of how it is. I added some examples for this talk. So for example, for rating prediction, you should really use very well-tuned matrix factorization, like SVD++ and like super basic methods. I would say a reproducibility paper is a really good starting point to identify a strong baseline, right? Because go to the paper that says, everything is worse than this simple method, use that method, right? That's a really good way to find a strong baseline. You should really test that. And now you might be saying, well, you had this quote, this cheesy quote at the start of like, we shouldn't chase wins, right? And now you come with the, you need strong baselines and state of the art and all of this shit. Right? And it's true. And I still echo the sentiment that we should chase insight over winning. But if we don't win, we shouldn't claim wins, right? So sometimes things just don't work out. So we should have a good idea and investigate it and report the results, even if they're bad. And that is obviously very idealistic. And there are no SIGAR reviewers. It's not easy, right? But it should be the aspiration, because otherwise, what are we doing anyways here, right? Or we should chase different goals, maybe not state of the art, maybe other goals beyond accuracy, right? I linked some goals in there. And this is like the next time your transformer model, which is not the model we reproduce, but the model we then continue to train on this, like for a very long time on a lot of data, it got still crushed by BN25. So this is a personal failure also, right? So you spend a lot of compute and a lot of work, and then you're still outperformed by BN25. And I linked you to the paper. So then we might just acknowledge that real progress in a certain field is just really, really hard, right? And we gain nothing by just being like, oh, we have state of the art, so please accept our paper, and we have state of the art, and everybody has state of the art at some point, right? So the point is still the same. We should develop insight, not understanding, even if it's delusionally idealistic. I get that. All right. The last part I want to emphasize, which makes our paper reproducible or not reproducible, is I think something really under discussed in the community. It happens in some papers, but really not a lot. I would say communication makes your paper and your work reproducible or not. What do I mean with that? Well, in a similar study that we've had before, authors were contacted that did not share their code. 14 authors, only 4 responded, right? Within 30 days. This makes your work not reproducible. Even if your code is out there, people might have questions. You should answer these questions, provide follow-up help, answer GitHub issues, are all things that enable reproducible research. And I would think this is a major problem in the current system because our current structures really don't incentivize this like long-term support of your work at all. You're basically, once you get the accept email, you're like, oh, there you go, I commit everything, I didn't clean everything up, my code is out there, so it's reproducible, it's great. And then you don't have to answer anything. Not everybody's like that. I had really, really, really positive experience with contacting authors. But I would urge everybody to think about communication and continuous communication about your work as part of reproducibility. All right, so let's talk about a few things that make reproducibility easier. Now, we talked a lot about problems. What are some fixes? I won't talk about everything. There are so many. And I'm ranting already for 40 minutes. So I linked a bit of an older blog post, but it's still very valid, from the organizers of the Machine Learning Reproducibility Challenge at NeurIPS here, which I think is really good. I'll talk about 5 points from this one. The first one is configuration management. So show of hands, how many people have an arc parse at the end of the project that just like this? At least a few honest people. Nice. Welcome. Yeah, I think everybody was there. Or they don't use arcparse, which is even more frightening. No, but so the thing is, at some point, we just have a lot of command line arguments, and then somebody reads your paper and is like, why is the weight decay 0.9? What did they try before? I don't understand, right? How did we even get here? And how do I train anything else? It's not the end of the world to use arcparse. That's not the point. But I would say for big projects, it gets really, really much easier if you use certain kind of configuration management. Now, everybody who knows me will be like, this is where you do the Hydra sales talk. Yes, maybe. But I would say it doesn't matter what framework you use. Use a file, store it in JSON, store it in YAML, maybe not CSV, but like store it somehow. It gets so much nicer. You can add comments, you can add ranges for stuff. You can compose hyperparameters. So for example, it's trivial to build a setup like this and load the best parameters per model per data set that you found through tuning, instead of just having these huge arcpaths that you need to edit in for every combination and these kind of things, right? So do this. You can have, you can compose things. You can have hyperparameter tuning integrated. You can even have parallel Slurm execution in these things integrated. And now we're getting back to the Hydra sales stuff. But I would really urge you, it's really helpful. Also, you can just say, well, all of our parameters are on Git in this folder, and then you have a huge folder with hyperparameters, and then you have all of your model dataset combinations. It's great. It's actually not the worst. It's better than to write a big, long paragraph in your paper, I would argue. Let's talk hyperparameter tuning. Heard about a lot already before in baselines. I won't endorse any black box hyperparameter tuning library here. I don't think there's one single way to tune your hyperparameters. I think the most interesting read on this topic, and it's a very long and complicated read, but I think it's worth a morning of yours, is the Google Deep Learning Tuning Playbook. It's a very nicely written blog post, and the basic idea is you should start with simple parameters and incrementally improve them. What does that mean? You should explore your hyperparameter space. For example, at the start through random search or grid search, meaning you should explore what matters in your parameter space. They divide parameters into scientific, nuisance, and fixed hyperparameters. What do they mean with this? Some parameters are fixed and you shouldn't tune them in the current round. For example, a batch size. A batch size isn't to be tuned for validation loss. It's tuned based on your GPU. How much stuff can you fit into memory? That's your batch size. And then you address, for example, the learning rate and these kind of things. For example, then scientific means this is the hyperparameter in the current round of tuning we want to understand, we want to find kind of the optimum for. Nuisance parameters are things we have to tune on the side. So for example, if you want to decide on how deep should your neural network be, the depth of your network interacts with your learning rate. So you can't just use learning rate, I don't know, 0.001 and then increase the depth of your model. No, you need to try different learning rates every time you kind of go deeper. And so this is super annoying, but this is why they're called nuisance parameters. This is kind of important to get down. And then you can step by step tune kind of your setup. And I would say only then use a black box optimizer that you kind of prefer, things like Optuna, Nevergrad or something, when you understand your parameters well. I wasted weeks, not that long ago, like last year, about like, I used things like Optuna and then you get hyperparameters and they work well. And then you run it again and you get completely different ones, but they also worked well and nothing made sense. In the end, I was fitting noise. Certain parameters didn't matter. And then I get a different, embedding size, even though everything above a certain threshold was fine. So this really is not a good way to just throw things into black boxes. Understand your parameters. And I think this is a reasonable way to go about it. Let's talk managing experiments. There's the similar thing. There is not one size fits all for tools. I think it's more get accustomed to things, what they can do for you. If you like one, use it. I think things like weights and biases or, I don't know, ML flow are super interesting to just track your experiments and most importantly, probably to observe your metrics in real time, share them with collaborators, get a push notification on your phone if things break, these kind of things, right? Have checkpoints of your models, data artifacts, some even integrate with your hyperparameter tuning libraries, right? So there are different features. They're all valuable. You don't need to use them. They typically make your life a little bit easier. When it comes to data management, I would say the number one rule for data management is don't. If you can, don't do your own data management. Use a library that somebody else built you. So for example, IR datasets is a very good library from yours truly, Sean, over there, and colleagues. So for certain datasets, they're already available and you can just download them and you can use them. And it's probably better than writing your own stuff at some point. Things are published on Hugging Face datasets. You can use them for recommender systems. There are libraries like Regbo that do a decent job of these things. If you need to publish your own data, make sure it's in a permanent location. Some institutions have like kind of permanent storages, but if they don't, Hugging Face datasets per repository allows you to upload like 300 gigabytes or something of data, which is a lot. And DVC, I think, is unlimited. So there are options out there. And then you should document the data set. So it does not matter, like there are so many different brandings on what you use, if it's Hugging Face dataset cards or Google data cards or data sheets, and it doesn't matter. They all have the same intuition. Write down, where does this data come from? What the hell is in this data? How was this pre-processed? Who are the users? Am I allowed to use this? What's the license? These kind of things, right? Make sure it's all there. All right. Similar idea for documenting your method and your model. If you release anything, make sure you include like who did what, licenses, architecture, risks of your model. Nowadays, also for certain transformer models, think about reporting carbon emissions, and only then think about like, oh, this is how you use my method, and here you should cite me. I linked a really good overview for the things you should include when you document the method before you release it. But there's many, many more things, right? So things about seeding, about dependency management, these were all in the first blog post that I linked. These are not things I covered today because it's too much at some point. The next thing I want to spend a little bit time on is okay, you do a reproducibility study. How do you write a reproducibility paper? The first thing about writing reproducibility papers is your reproducibility paper should be reproducible. It sounds insanely trivial. It is not. This is a review from the ML Reproducibility Challenge 2 years ago, where authors found great mistakes in the original work and then repeated completely the same mistakes, like did not release their data, did not describe how they got their data. All of the things where we would say like, oh, this is not reproducible, they did that. So it's not great. And what I was surprised by, but I think it's a good thing, at this year's Rexis, it's a desk rejection reason. So if you write a reproducibility paper and you don't release all of your code, all of your data, you get desk rejected. So it's really important, right? The next thing is a little bit about what to reproduce, what to look into. And I would say in short, new and important lessons. So this is from the SIG-IR call of papers. So it's about their interest in reproducibility rather than replicability. So an existing method on a different setup to learn some lessons that generalize rather than just some team being like, we really run the same code and we found different results. This is not that interesting, right? I would say key points to consider, they were mentioned in all of the big reproducibility conferences right now, were novelty. So is your setup that you're applying this method to novel? Or are the findings that you have now novel, or are they already known in the community? Which lessons generalize from the original work, which don't? That's super interesting. And then impact of your work, right? How interesting, how important is this for the IR community? And I would say, given that people judge papers based on that, write sections on that. Literally have a tiny paragraph that says impact for the IR community to make it as easy as possible for a reviewer to understand why things are important. They might be clear to you, not to every reviewer, right? So it's really helpful to sometimes be really on the nose and like, and this is where it's impactful. Like really do that. And this is now with a big disclaimer, like everything so far has been opinion, but I think this is even more with an asterisk because I'm not an organizer of a reproducibility track or a professor who has done this for like 30 years. This is a personal opinion, but I think it's an observation I've had now with multiple colleagues. I personally think there is a fine line that reproducibility work always tends to tread. It's the line between lack of novelty, where you get a review back where people are like, well, just rerun the code, or the findings are already known, this is not interesting enough. And then the thing of like too much novelty. You find a problem and you instantly, for example, write a fix for that problem or propose a new method, or here's how we do it better. And then people are like, this is not a reproducibility paper anymore. This is a method paper. This should go to the long paper track, right? And then you're sitting there and being like, well, but it started out as a reproducibility paper. So I think the main novelty of your work should be the lessons learned from the reproduction. And if you find yourself proposing too much novelty in the same paper, maybe consider splitting things or writing a follow-up paper. And if you're unsure, there are really good reproducibility papers out there, and read a few to see kind of where's the line. There is not a good answer to this. It's just a thing I feel is happening. The last point I want to mention on communication kind of is how you phrase a reproducibility paper. And always keep in mind that everybody, all of us, constantly make mistakes, right? So the first thing is you should always try to involve the original authors in the process. Ask them for code, ask them for questions, discuss your findings, send a manuscript if they answer in a reasonable amount of time. You can't be two days before the conference like, hey, by the way, we found this, and then they don't answer, and then you can write in your paper like, and they did not even reply. Like, don't do this, right? But I personally, honestly, when my supervisor first suggested this, I was like, yeah, I'm not sure if we need the authors. Like, I don't want to, because it's uncomfortable, right? You write somebody of like, hey, by the way, we find your entire Europe's paper is below random. Like, it's an uncomfortable email to write. It is really great, honestly. Like, not always, I get that. But for example, in my specific case, the people were insanely forthcoming. They owned up to all of the mistakes, provided way more detail than they had in the paper, and they made the reproducibility paper much better. So like, do that. It's sometimes surprising how nice people can be. Then similar notion, I would say the golden rule of reproducibility papers is like always consider you have written the original work. So are you comfortable with all of the statements, all of the things you're phrasing when they would be said about you, right? So sometimes people can be a bit too like, haha, look at those stupid people that did all of these mistakes, right? And how smart am I that I found these? So be careful about how you phrase things. And this is also kind of echoed in the last part in like a different version of Hanlon's razor. So it's never attribute to malice which can be adequately explained by neglect, ignorance, or incompetence. The original version is a bit unfriendlier, but we chose to take this one. So this is basically always assume the best intentions. If you find a mistake, don't assume fraud. Assume people made an honest mistake. It can happen. It happens to all of us constantly, right? All right. For the last few minutes, I can't talk about reproducibility in the IR community without talking about reproducibility in the tradition in the IR community, because there's a lot. I don't want to glass over this and just be like, oh, there are so many problems and we're so bad at reproducing stuff. We're not actually. Like you've heard a lot of these things, so I won't go over them today anymore. But essentially, the first works in IR with the Cranfield collections were reproducibility works. It was literally somebody sitting down at a library and being like, all of these different systems are being proposed. We need a test collection to figure out which method works well. That's kind of a reproducibility paper, right? And there we got this notion of we need queries, we need documents, we need relevance judgments. Track introduced pooling that you've heard about today, right? Where you just submit results and then they get judged. And it's huge now, right? It runs for over 30 years. We have a bunch of search tasks, domains, and feedback. NTCIR is also a long-running thing for East Asian languages by now. We have CLEF, which is more for multilingual and very multimodal and really diverse kind of search tasks. FIRE for Indian languages, and we have Center now, which is kind of the reproducibility track for the most interesting work at CLEF, NTCIR, and track, kind of mushed together in the worst acronym I've seen in a long time. But yeah, that's this one for you. So these are all big, long-standing conferences or tracks where people tend to, work on collective benchmark data sets and also reproduce a lot of work. But if we remember the beginning, the improvements don't add up paper, this was conducted on track data sets, actually. So somebody looked at track data sets and found no improvement over 10 years. So track did not prevent this from happening. It helped us to uncover these things, granted, but it also did not, there are 10 years of basically no progress in ad hoc retrieval. So why did this happen? And can we do something better? And what the authors in the original paper suggested were basically leaderboards. And we had a bunch of leaderboards and competitions since. We also had some before, but essentially leaderboards and competitions not only unify the data sets, but they enforce common baselines and they enforce a common evaluation procedure, right? Somebody else evaluates your stuff, which is really good. Most prominently in recommender systems is the Netflix prize, where Netflix was just like, $1 million to the person who can beat our production system by 10%. It took 3 years, but somebody got in the end $1 million and donated this to charity. But this was a lot of really strong methods that in the end kind of, are still common today, and you will find today in reproducibility studies that they're working so well. They came from this kind of phase. You have things like MS Marco, right? The leaderboard for passage re-ranking, question answering, and NLP, which was stopped, I think, last year, but it really, I would say, fostered a lot of research in neural IR. Now you have things like BEER, which is benchmarking for zero-shot retrieval. So basically, you train a transformer on one data set, and then you confront it with rankings on a slightly different domain or these kind of things, right? So out of domain zero-shot generalization here. All of them very incomplete list. There's way more. But the point is here that leaderboards are really helpful to force kind of a common progress in fields. All right, let's conclude this. It has been long enough, I think. So concluding, reproducibility, I would argue, is really at the heart of scientific progress. And it has already a very long tradition in IR. And I think if there's one point of today's talk, then it's the takeaway that producing truly reproducible work is really complex. It's very labor intensive. It's really annoying also sometimes. And it's has much more to it than just being like, here is my code. My code or some of my code is on GitHub, right? So it's really more of a complicated thing. Select simple and strong baselines and tune everything with care and also report what you tuned, right? There are some tools that can make your reproducibility studies easier, but in the end, it comes really down to publishing clear, open, and detailed research, and to then not publish things and go away, but to stay in constant exchange with your peers and be connected to your work, right? And when conducting reproducible work yourself, focus on the novelty of a method, how generalizable the findings are, the impact of your work. And lastly, always, I would say, try to involve the original authors. And with that, I thank you. The rant is over. And if there are any questions, I'm happy to take them. Thanks. Yes.
You mentioned on the gaming side you are doing like research a lot.
If I'm doing research? Yeah.
You are?
Sometimes, yes.
Sometimes?
Yeah.
Because of new architectures research, what are you searching for?
Well, the thing is like sometimes, okay, so sometimes it depends really how restricted you are in, I would say, in your computational budget, right? So I think the best thing to do is something like a quasi-random search, where you do random search, but you try to enforce a certain kind of intervals, which is great. But sometimes if you can run like 3-4 things, then it's literally like maybe like equally distant intervals of something like that. Or it's also not the worst to just be like, we try these 4 different embedding sizes that have been shown to matter before, like a lot of times. But then I would say, for example, it depends on your task. But in my previous work, for example, it was way more important to run a method over 5 different random seeds to find a hyperparameter than to try 5 different hyperparameters, because it was so noisy, right? So it really depends on your task, what you try to allocate your computational budget for. And sometimes a really stupid grid search where like we try these 4 different embedding sizes, but then 5 times might be, I think, still worthwhile, even though obviously it's not the golden standard, but it helps you to understand your parameter space a little
bit. Learning data.
Yes.
Already has optimizers. So Adam.
If you use Adam.
Yeah.
Yeah.
So you need that.
You need to find for Adam the lowest, the base learning rate. Yeah. So you need to.
Other than that, you can just say, for embedding sizes, it's interesting. So how do you like select the range? So for example, forget the layer part.
Yeah. Yeah.
For embedding sizes, how do you do that?
Incrementally find like an upper bound where you have like no improvement anymore, or find what is just really too slow. Like for example, I had like embedding sizes like something between, let's say, 32 embeddings and like 1024, and then you pick something and then you see what you can feasibly compute. It's also perfectly fine, I think, to restrict a method based on runtime and things like that, right? You don't need to find the perfect parameters, but you should, in your clearly defined ranges, find the best parameters. And this is then one way to do this, I think.
Because I was going to say, like, I used to do research when sklearn was there.
Yeah.
Then I don't do research anymore.
How do you tune your parameters?
I just learning rates. Yeah, sure. Like for example, embedding sizes. I know exactly what you're saying. But it's not really like the auto grid search parameters if you can use like sklearn. And even then, I remember that used to take a long time to learn like SVM.
Yeah. But for example, here in the setting, I also didn't say like do full grid search, but for example, you can do incremental things. There are certain parameters you can tune in order, and then then you really need to make sure that you arrive at these things. So for example, if you tune over multiple things, you can perfectly fine first say like, how deep should my network would be, or how wide should it be, and then like do step-by-step things, right? This is not, I'm not a transformer person. I think there is way less tuned, but like if you have just like deep-forward neural networks, there are certain step-by-step things you can do.
Deep-forward neural is easier, but for transformers, it's a little bit harder to do because again, like the number of combinations of hyperparameters that you can generate versus training time or fine-tuning time.
Yeah. No, but we also still we tuned hyperparameters for transformers also a bit, at least. You can do that, and there's papers without a Roberta paper is not uninfluential without any reason. That was just good because they looked at like, no, these things matter, these things don't. So you should still try to do that, the things that matter for your approach.
Yeah, it's going to flow because in transformers specifically, right, you have the base Roberta, it's basically base Roberta of all the models. But if you drop certain layers, you lose certain weights. So technically, what you should do is have an architecture, you drop certain layers, and then probably you should pre-train what exact pre-training X long. And all our resources. So it's a little bit more constrained. Even if you start dropping layers, unless you distill them.
We halved the time to train our bird transformer by using JAX, and it's not as horrible as it sounds. Like there are certain things you can do to if you have a certain compute budget, and you know it depends what matters in your setup. All right. Yes.
I just have a question or a comment. Like, what is your comment on right now? If any paper is saying, okay, they have used n number of V100 GPUs or these things for training.
Yeah.
And it is not reproducible, though they have provided the hardware requirements, but not everyone will have that much of hardware.
Yeah, this is a super important or interesting point that I left out of this, but there are papers that discuss this. You can publish, and I would say this happens a lot of times nowadays, you can publish non-reproducible work by compute budget. If Facebook trains on 100,000 GPUs or something and says we did this on 100,000 GPUs, then you're like, thank you very much. Nobody will reproduce this way, right? We can use it. We can see if we get similar results. Yes, of course. If that happens, I don't know what the recommendation is. You probably then should evaluate what is the goal of the paper, right? Is the goal of the paper that they release some model that people can use and they invested all of this compute, then it's fine. If their goal is, this is a method you can run at home, but only on, 100 H100s or something like that, then you're like, oh, well, thank you. Maybe, try something else or release something that people can use more easily. So I think it depends on the context and the goal of the paper, if it makes sense. Yes.
Do you think there should be a timeline for which a code and the paper is reproducible? For example, like I've been looking at some clustering papers that were written in 2014, 15. They were written in Cafe or Piano libraries. So the code is sure as not reproducible right now in 24. But I don't think that the responsibility lies on the authors now, like to go back and convert the code to a newer platform.
It's true if it depends on a thing where you can. It depends, right? So if you write everything in a certain language that is now not supported anymore, right? I wouldn't force anybody from 20 years ago to be like, hey, just re-implement your stuff now in Python 3.11 because the old version is not there anymore. That doesn't make a lot of sense, right? But you should still structure your code in a way that makes it reproducible for a long time. Like, for example, if you don't have fixed versions, but just say we use PyTorch and we use this and use this, this will surely break in a year or two, right? If people can't go back. So if you want to be very extreme, some people are like, no, you should always do, Dockerize your stuff so people can run for a long time. I'm not on that front, right? So surely I agree there is a certain reasonable support you should have. But for example, there's still in my field people that run like 20-year-old code in SVM rank written by hand in C++ from some professor now. Like, it's really weird. Some things are just, stay in the community for a long time. Some things will stay very easily. Maybe as a last recommendation, don't use insanely hyped languages where you don't know, like, I'm not sure if they will be supported in a few years, right? Don't maybe write your entire research with that. Maybe if you want to have a broad audience, then pick the most basic stuff like Python, right? So that's also maybe a consideration. If you go very niche, it will be less reproducible.
But not all the blame lies on researchers in that case. Like
No.
C++ code is it will be easy to run than the TensorFlow 1.0 code, from my experience.
Yeah.
But some part of that blame lies on the Google, I would say, the TensorFlow debacle that happened with 1.0 that they were not able to do.
For sure. But for example, I was a Java developer for a long time. Then Kotlin came out. Is the first thing I would do to write my big paper now Kotlin? No. But nowadays I see, okay, it has much more support. It's a more secure base. maybe it's interesting for people again, right? But like when it just came out, then you shouldn't just be like, oh my God, look at this awesome language. I'll do everything in this. But I agree, it's not the blame's all on the author. All right, maybe let's take the rest offline. Thank you so much for listening. We are over time already. Have a lovely boat ride tonight, I guess. That's and hackathon now, I think. Andrew? No. Maybe as a last thing, I do half of the things that are in this talk, right? I don't want to come across like I never do these things. Everybody does it in some way, so it shouldn't be like... Anyways, Mohammed, thank you.